Just the I don't want to.
No.
Is that right?
I like spread, so it's there.
Yeah.
Like that, and the brain, like this. No, it's certainly building the wrong like stuff. Complex. Your brain stops. You carry a certain amount. That's something, then you're not good. And I like people who can think and do things.
Yeah.
I do.
Tutorials.
Back into
Okay, we have two more tests, conversions tests to talk through, and then we'll need to revisit some of the problems that we skipped over from the absolute and conditional conversions notes, because we haven't done ratio tests yet. So we'll talk about ratio and root tests. We'll go back to 10.5, the problems that we skipped over, and then we can try to put it all together in terms of identifying the tests and being able to know which test for which problem. Let me start off with this here. Factorials. Has that exclamation mark there, and that just indicates we're multiplying a bunch of numbers from that number all the way down to 1. Okay, so factorial, 5 factorial would just be 5 times 4 times 3 times 2 times 1. Likewise, if I have something that is in the form of n plus 2 factorial, I can write that as n plus 2 times n plus 1 times n factorial. Sometimes being able to break a factorial down into separate parts allows us to match and cancel out a little better. So that's an example of factorial down to n factorial there. Because then n factorial would be n times n minus 1 times n minus 2, okay, all the way down to 1. So here, if I have n plus 1 factorial over n factorial, I can basically clean up the numerator in a way that will allow me to match and cancel out with the denominator. So n plus 1 factorial is equivalent to what? N plus 1. Mm-hmm. Right, but we just have to go as far as matching the denominator. Once we find a match to the denominator, we can stop, because that allows us to reduce. That makes sense. N plus 1 factorial, same thing as n plus 1 times n factorial. We good with that? Okay. So this allows us to reduce, and we're looking at n plus 1. Likewise, 3 to the n plus 1 over 3 to the n. I think we know how to reduce this here. We can separate them into product of bases. 3 to the n plus 1 is the same thing as 3 to the n times 3 to the 1, 3 to the first power, and that's the same thing as equal to just 3. Okay, so here's the ratio test. Ratio test says if my series from 1 to infinity of a sub n has positive terms, and the limit as n approaches infinity for the a sub n plus first term divided by a sub n, all this is doing is we're replacing every n with n plus 1 to create that n plus first term. If the n plus first term divided by a sub n is less than 1, then we know that the series converges by the root test. Sorry, not root test, ratio test. Root test is next page. And we're always having to do the n plus first divided by a sub n. So it's important that the order is correct. It's always a sub n plus 1 divided by a sub n. If the limit as n approaches infinity of a sub n plus 1 over a sub n is more than 1, then we can say that the series diverges. And then if it's equal to 1, then the ratio test is inconclusive. Meaning that we don't know one way or the other. We have to rely on a different test. Okay, let's look at series that we already know. Now, these are not ones that we would normally want to do ratio test with because we already know what this is going to be. Harmonic series, right? We already know this is going to do what?
Okay.
This is going to diverge. But just to demonstrate what ratio test would look like in terms of the setup, we would do the limit as n approaches infinity of a sub n plus 1. So a sub n plus 1 just means every n that you see, replace it with n plus 1. And then you're going to divide it by the original rule of sequence. Okay. Dividing by a fraction, the same thing as multiplying by the reciprocal. So this is equal to what? 1. And then, yeah, n over n plus 1. And we know that limit as n approaches infinity, degrees match. I'm just left with 1. And then this one, the ratio test is not good because it's inconclusive. Okay, we're just doing this just to show what the results would look like in terms of something that's inconclusive. And then same thing here, 1 over n squared. Normally, we would know that this is just a converging series because it's p series, right? But just to practice the setup for ratio test, a sub n plus 1 would look like what? Yep. And we're going to get into a habit where instead of writing this out, dividing by a sub n, it's just going to make it faster if we just always know that, okay, I'm always going to multiply by the reciprocal. I'll save some steps here. And then if we do n approaches infinity, what's that equal to? 1, right? And 1 is still inconclusive in this case as well by the ratio test. But there's a certain look in terms of when to use the ratio test. And typically, if we see a bunch of exponent variables or factorials, those are typically good setups for us to kind of lead us towards ratio test. So we can kind of point those out here. If you look at number 3, 4, and 5, you see this one has a bunch of exponent variables. This one has exponent variable and factorials, and this one has factorial. So anytime I see a combination of either factorial or exponent variables, typically ratio test is the one that will be the best fit for those problems. Okay, so let's look at number 3 here. Number 3 says use a ratio test to find convergence or divergence. So we're going to do limit as n approaches infinity of a sub n plus 1. So we're going to create the a sub n plus first term. Every n that we see replace with n plus 1. So I'll put an absolute value here because technically they should be living inside absolute value bars. So n squared becomes what? N plus 1 squared. 3 to the n plus 1 becomes what? n plus 2, right? The n becomes n plus 1, and n plus 1 is n plus 2. And then the 5 to the n becomes 5 to the n plus 1. Now, technically, we're dividing this by a sub n, but we're always just going to make it easier on us. Let's skip a step here and just multiply by the reciprocal. Okay. Are we okay with the setup that the step I'm skipping? Are we okay with that? So rather than dividing by a sub n, I'm just going to skip this step and just go to my multiplying by the reciprocal of a sub n. So I'm going to try and line everything up here in terms of I want to try to get as much canceling done as I can before I evaluate my limit. So to help us with that, I'm going to kind of separate the parts so I can kind of see the like terms a little bit better here. And also I'm going to group the n plus 1 and n plus n squared together. Okay, I'm going to put all the, so. Okay, so this is what I'm going to do here. I'm going to put everything under one fraction. 3 to the n plus 2 is same thing as 3 to the n times 3 squared times 5 to the n. I'm going to separate that n plus 1 squared from the rest because I'm not going to quite cancel that out. Now, denominator, I have 5 to the n times 5 to the first power times 3 to the n times 3 to the first power. I'm going to group the n plus 1 and n plus n squared together. Make sure I have everything here. I'm just rearranging things to allow for me to group things together. Are we okay so far? All right, let's see if we can do some canceling out here. What can we take out easily here?
5 to the
Yeah.
n.
3 to the n.
3 squared becomes 3.
Yeah. 3 squared becomes 3. So I'm just left with 3/5, right? 3/5 is my leftover. And then what's the limit of this going to be? It's 1, right? N squared over n squared. My degrees match. This is going to just become 1. So the only thing left over is what? 3 over 5. Now, we're going to look at this and compare it with these options here. What is 3/5? Is it less than 1 or greater than 1 or equal to 1? Less than 1. So therefore, we can say by ratio test, this series converge. Let's write it out. Let's write it out. Yeah. Converge by ratio test. All right, let's try number 4. All right, every n I'm going to replace with n plus 1. Dividing by a sub n is the same thing as multiplying by the reciprocal of a sub n. Now I'm going to try to break things apart and separate and see what I can see what's left over after some cleanup. I'm separating everything into individual parts enough for things to cancel out more easily for me. So what can I remove here?
Factorial.
Okay, what else?
4 to the n.
And 4 to the n. So I'm just left with 4 over n plus 1. What's going to happen to this fraction? The limit as n approaches infinity for 4 over n plus 1 would just be what? 0, right? That 4 is going to stay a constant. This denominator is going to go to infinity. 4 over infinity is basically 0. And then what can we conclude? 0 is less than 1. Therefore, series converges by ratio test. Yeah. Okay, side note, if you guys can put this down here, ratio tests usually good for fractional functions involving exponents and or factorials. Like 4 to the n, 3 to the n, 5 to the n factorial. Anytime I see those, especially when I see factorial, it's a guaranteed that, okay, I'm always going to go to ratio tests if I see factorials. And most of the time when I see exponents, I'm also thinking about ratio test. Unless it's something like 3 to the n over 5 to the n, then I'm just thinking, okay, I just get that into ratio test form. But if something looks more complicated than ratio test, if I see 3 to the n over 5 to the n, then that's an easy geometric series for me to recognize. But if something looks more complicated than geometric series, then my go-to is ratio test. Okay, let's look at number 5. All right, replace every n with n plus 1. Now, careful here. When I replace n plus 1, I need that 2 in front of it. I want to rewrite this. So 2n plus 1 is really 2n plus 2 parentheses factorial, right? So I'm going to write it that way here. Times the reciprocal of my a sub n. Oh, darn, you're right. Thank you. Okay, let's clean some things up. We can't do much with the n plus 1 to the 5th and n to the 5th. We know what's going to happen there, but we do want to try to get the factorials kind of lined up a little bit better here. So 2n plus 2 factorial, same thing as 2n plus 2 times 2n plus 1 times 2n factorial.
So for just 2n factorial, you can split the 2 in the n, or
I could, but I don't need to since I already see a matching pair with my denominator. Okay, I'm just putting the n to the 5th and n plus 1 to the 5th together here. All right, what can we cancel out here? 2n factorial. Okay. This is just going to equal what? Equal 1. So I'm just left with 2n plus 2 times 2n plus 1. Now the limit as n approaches infinity of 2n plus 2 times 2n plus 1 is just going to be what? It's going to be infinity. So that's obviously greater than 1. So we know this diverges.
Mr. Yang.
Mm-hmm.
For the limits, do you have to say what the limit will equal, or can you just say that it's greater than, like, do we have to put that it equals infinity and that it's greater than?
We don't have to, no.
Okay.
No. Actually, yeah, you know what? I do want you to show me what you're comparing with. So I do want to see that your results compare with 1. So I do want to see. yeah, sorry, I do want to see that additional step. Okay, let's talk about the root test. Root test has a very similar feel to ratio test, but I think it's a little bit easier. Let's go to page 49. Okay, so the final test to determine convergence or divergence is the root test. Root test is especially well suited to solve problems involving nth powers. So it resembles ratio tests in some ways. This is really good for when the entire rule of sequence can be written as a power of n. If I can rewrite the entire rule of sequence and raise everything up to the power of n, then it's a really good fit for root test. So what we can do is, if everything is raised to the power of n, we can do the limit as n approaches infinity and take the nth root of that expression. If we take the nth root of that expression, it'll just basically wipe out the nth power, it'll wipe out the nth root, and we're just looking at what's inside the parentheses. And we just simply look, does that series, does the limit of that rule of sequence go either towards 1, or is it greater than 1, less than 1, or is it inconclusive? So the conditions is going to be similar to your ratio test in terms of what you're comparing to. You're comparing with 1. Is it greater than 1, less than 1, or equal to 1? And it's the same idea. Less than 1 is convergence. Greater than 1 is divergent, and then equal to 1 is inconclusive. All right, so let me show you what that looks like. So it says using root test. The nice thing here is we know something is a good fit for the root test. If I can rewrite my expression, you just raise everything to the nth power. Okay, that's a good sign. We see that root test is going to be the best fit. So what we can do is we can do the limit as n approaches infinity of the nth root of what we see there. So the nice thing about that nth root is, what's it going to do? Yeah, it's going to wipe out that n, and we're just looking at what's inside the parentheses now to determine convergence, or what that limit is equal to. And here, as n approaches infinity, and e squared is just a number, what is this going to approach? 0. And 0 is less than 1, so converges by the root test. Let me skip number 8. This one is not a, yeah, sorry, yeah, we'll do number 7, but we'll skip number 8 eventually. Hey, number 7 is kind of a giveaway, right? This whole expression is raised to the nth power. If I do the root test, I can just, basically, I'm just dealing with what's inside here. So that makes it a nice, easy problem once we get that n out of the way. And you always want to take the absolute value so that we can really compare with 1. So what is this equal to?
0.
0 over 2. And 3 over 2 is greater than 1, so therefore diverges. Okay, let's skip number 8. There's a better test than we wouldn't normally do root tests because we can't raise everything to the nth power. So if we can't raise everything to the nth power, even though it's doable by root test, we're going to try to find an easier test for something that's that we can't raise everything up to the nth power. So number 9, this one's a good fit for root test if I just rearrange the exponent with the denominator.
Does factorial go faster than
Yes, factorial grows faster than polynomial.
does it go faster?
Yes, it does. Factorial grows faster than exponents as well. Okay, try number 10.
That's good ruler, like it doesn't matter.
Yeah, just so that we can see that that we're applying the root test. Are you talking about like this nth root?
Yeah, that's not really doing anything.
It's not doing anything, but we are showing that this is the proper step for root test, right? That because we're doing this, we're allowed to just look at what's inside.
Oh.
Right. Okay, let's go to back to page 37. We skipped over some of the problems from the absolute versus conditional convergence because we didn't know how to do ratio tests, but now that we know, we can deal with those factorials and exponential problems a little better. Okay, page 37. All right, so number 1. So number 1, it says find if the series converge absolutely, conditionally, or whether it's divergent. So I'm gonna move the negative out of the way because if we want to test absolute convergence, we can just focus on the rule of sequence without the alternator. The same thing as -1 to the n times 3 to the n. So I'm just focusing on that 3 to the n over n factorial. And anytime I see factorial, I'm just always going to look at ratio test to help us out there. So we'll do ratio test here. Page 37. So it's always a sub n plus 1 divided by a sub n. We're just going to multiply by the reciprocal of a sub n. Do some cleanup. I'm I have it out of order here, but okay, let's do some canceling out, some reducing here. 3 to the n goes away, n factorial goes away. I'm left with 3 over n plus 1. Limit as n approaches infinity, that fraction is going to go to what? 0, and 0 is less than 1. So without the alternator, without the help of the alternator, this is already going to converge. So if it converges without the alternating term, then we can say that this series converges for absolute convergence, right? Okay, numbers 4 and 5, let's go through those as well. Same page, page 37. This one's a little bit different here. It says, find the values of x that makes the series converge absolutely. What we're going to happen is that when we find the limit, the x is not going to go anywhere. It's n approaching infinity. So whatever is left over, we're just going to have to fit it into our rule. Let me show you what that looks like. And this is going to be useful for our after the test when we talk about when our series will converge. So just it's kind of a bit of a preview as well into what we're going to do a lot of next half unit. Okay, so I see a bunch of exponents. I'm going to apply using ratio test. So I'm going to ignore the alternator. It's just going to be the positive portion here. So every n I see replaced with n plus 1. Multiply by the reciprocal. Okay, we want to make this series converge, yes.
Why couldn't we get-
I'm sorry?
why couldn't we do?
Because we can't represent this n. It's hard to represent this n as raised to the nth power. Because this n raised to the first power. Yeah.
So if that n was raised to the n power, root test would work.
Yeah. Okay, so let's do some cleanup here. let's do some reducing here. X plus 4 to the n cancels out. 6 to the n cancels out. The n and n plus 1, what's going to happen here? Just becomes 1, right? So I can reduce that as well. So I'm just left with absolute value of x plus 4 over 6 is less than 1. So we're basically trying to figure out what are the values of x that will make this series converge. I'm going to bleed into number 5 here a little bit, the space for number 5. But this is what I have left. I have absolute value of x plus 4 over 6 is less than 1. This is the leftover, right? We know that this is n approaches infinity. The x is not going to have any, is not going to be influenced by n. It's just going to kind of stay there. Are we okay up to this stage? So I'm going to cross multiply basically. I'm going to move that 6 over to the right side. I'm going to make it absolute value of x plus 4 is less than 6. Are we okay up to this stage here? Now, to rewrite this, because this is basically saying that x plus 4 is between -6 and +6. So if we want to rewrite this without the absolute value bar, we would have to say -6, or that x plus 4 lives between -6 and +6. And we just have to solve, get that x by itself. I could just do what to every term here to get that x by itself. Subtract 4 from every side. So -10 is less than x is less than 2. So as long as x is between -10 and 2, we're going to safely be able to ensure that this series is going to be producing a value less than 1. And we can say for certain that our series will converge absolutely, or absolute convergence, when x is between -10 and 2. I'm going to use all the space for number 5 here. Okay. So again, I'm going to go through a ratio test for number 5. Every n I see replaced with n plus 1. Multiply by the reciprocal of a sub n. X will be left over, but let's see what happens with the n's. N and n plus 1 cancels out nicely for us. What else? X minus 1 to the n cancels out. I'm just left with x minus 1. The way that we can deal with that absolute value bar or undo that absolute value bar, we should make sure that this value sits between -1 and 1. Add 1 to everything, get that x by itself. So we're going to experience convergence as long as x lives between 0 and 2. Huh?
It's x equals.
Well, it could be decimals too.
Oh,
Right. Yeah.
For number 4, you consider n to be a coefficient. Can you think of the x plus 4 over 6 to be the part of a geometric series or no?
I don't think, yeah, we can't push that n out as a coefficient. It's a variable. So it needs to be part of my rule of sequence. Yeah. Okay, I'm running out of time here. I'll there's a little bit more I want to talk about with number 5. But your homework tonight is just page 50 to 55. 50 to 55. All right, come get your phones.
All I did was with, so like that's like, I might. But it's not, that's very good. Yeah, I'll leave it in. Don't forget. That's all I did. Let's just do that. If I do it in there, I have to purchase. But I want to, because I'm going to take this now regardless.